Okay, so good day, everyone, and welcome to our weekly session of our Imaging seminar. It's our pleasure today having Professor Martin Burger as a speaker. So Martin obtained his PhD in 2000 at the Johannes Kepler University in Linz. And he was then an assistant professor at UCLA and in Linz before becoming full professor in applied mathematics at the WWU in Münster in 2006. And since 2018, he's a professor at the FAU Erlangen. His research is very well known and focuses in the fields of inverse problems, nonlinear models for mathematical imaging, partial differential equations, and on the development of mathematical models in the life and social science, in particular with applications to biomedical imaging. Martin received several awards and honors for his scientific contributions, such as the Calderon Prize for his distinguished contributions in the field of inverse problems and the ANIRC Consolidator Grant in 2013. He serves in the editorial board of several journals, such as the GMIV and the Inverse Problems and Imaging Journal, and is one of the editor-in-chief of the European Journal of Applied Mathematics. His talk today will be on nonlinear spectral decompositions in imaging and inverse problems. And as always, I invite everyone to write questions in the chat or using the Q&A button of the Zoom window. And I'll keep an eye on that. So feel free to ask questions even during the talk and I read them to Martin. And Martin, whenever you want.
Okay, so let me just check if that works. Yes. Okay, thanks for the invitation and the opportunity to talk a bit about the work we did on nonlinear spectral decomposition, as we call it. This is joint work with many people. Maybe I don't read all the names, just mention those who were particularly important for it. In the beginning, this was started on our side together with Martin Benning in a paper we wrote for the special issue of Stan Osher's 70th birthday, where we introduced some concept of nonlinear eigen or singular vectors for inverse problems and imaging problems. And then there was parallel development by Guy Gilboa, which we then joined together and which I will tell you a bit today. There was Michael Möller for a while and still now was driving that strongly. And in the last 3 years, 2.5 years, the main driver of that field was Leon Bungert, who just finished his PhD with distinction in Erlangen. And I will tell you a lot also about results that were part of his PhD thesis. Maybe later I will forget to mention that, so now you have heard it. So let me just start with something that all of you probably know. Fourier decomposition, or somehow the mother of all spectral decomposition. Like in music, you decompose typical audio signal into some Fourier coefficients, and that's kind of the basis of all music theory, that you have this kind of discrete spectral representation that you see on the right-hand side for a sound wave, like here, in this case, for a guitar string. It's not always so much appreciated by musicians that you have this theoretical basis, but at least by mathematicians, it is a lot. And the Fourier decomposition, the Fourier series, is a spectral decomposition in the sense that it's a decomposition into eigenfunctions of the Laplacian. So in this case, it's an orthogonal decomposition. And this is not an accident, since there is some physics behind. All the acoustics is modeled by the wave equation, or in the quasi-stationary setting by the Helmholtz equation. And that naturally introduces the Laplace operator as the fundamental operator for which you can do spectral decomposition. And there is a lot of tasks that you can do with it. For example, you can, all the basic analysis of tones or music, you can do filtering. You can do something I have to mention in particular, since I'm in Erlangen, since MP3 was invented here, and there is the Fraunhofer Institute, which has actually a lot of money just because of MP3. So signal compression is something that is very natural based on spectral decomposition, and you can also do all kinds of quantitative analysis based on those. If you do inverse problems, or if you do any course on inverse problems, maybe the first thing, one of the first things you learn about the theoretical basis is you have a problem KU equals F, and you learn how to do a singular value decomposition, or maybe many people do that even in basic numerical analysis classes. And Gilbert Strang is always claiming a linear algebra class is good only if it mentions singular value decompositions. So in order to have a good talk, I also need to mention this, of course. So the singular values and singular vectors are a system of vectors or elements in some Hilbert space between which K maps, which have this kind of relation. So if you have KU, you get sigma times V, and if you have K adjoint V, you get sigma times U. So sigma squared is an eigenvalue of the positive definite operator K star K or KK star. That's something that is easy to understand and is very natural to do. Now the question nowadays arises, how would we do that for other structures, in particular for images? And with many data science applications now also increasingly this question is asked for graphs or graph-like structure, like in social networks or in some other cases. You would like to use these kind of techniques to decompose or analyze these kind of data as well. The problem is there is no kind of wave equation for images or no wave equation for graphs. So there is no physics basis on what to use and from which to do a spectral decomposition. And in particular, in imaging, it's known that solving things like based on the Laplacian is too much smoothing. So you would like to have rather non-linear problems, non-linear operators, which you use in order to define a spectral decomposition. Okay. So there are some attempts to do some kind of linear decomposition or orthogonal decomposition. So there is like a lot in wavelets and other related system, which have some kind of success, but still there are some issues. There is no kind of spectral really inside. It's an orthogonal or overcomplete decomposition. But one problem is, from a fundamental point of view, you would like to have simple images to have a simple spectrum, like you would have simple tones in music to have a simple spectrum. But if you consider this system, very simple geometric structures, images of a ball, for example, a white ball on black background or vice versa, they have a very dense spectrum in this system. So it's not what you would expect naturally from your intuitive view on images. And same on graphs. On graph, the graph Laplacian is of course very popular, and spectral clustering is nowadays a standard technique. And particular computing eigenvectors or eigenfunctions, in the sense of functions on a graph, of the graph Laplacian is something that has been used quite a lot, but it's not always that successful. So let me just show you. In this example, there is, unfortunately, I don't know why on the slides now the P is missing. So from left to right in this half moon example, you should start here with P equals 2 and then decrease P until you arrive at P equals 1 here. So what is computed here is on these data sets where you have built a graph that is depicted here, is an eigenfunction of the graph P Laplacian. So P equals 2 is the linear graph Laplacian, and you see it's a very, a very unsatisfying result of a clustering. It's not clustering really the two half moons. And you see it also from the histograms. Whereas if you go to P equals 1, it gets much more successful. So that again motivates all these kinds of one norm-based techniques, one Laplacian or total variation type techniques. And since we have Christmas approaching, of course, it's you can also see that in kind of real life applications. So like in Austria, we used to make some cookies for Christmas, like this vanille Kipferl. I'm not sure how to translate it. Maybe Carola has some suggestion. And so one of my postdocs wanted to make use of the expensive VR equipment we have bought. So he was sampling randomly points from this vanilla Kipferl and then tried to cluster this. So this is what he got. And this is a nearest neighbor graph he was assembling from it. And then the question is, of course, again, can you separate the vanilla Kipferl? And it's the same problem as before. If you do it with the linear graph Laplacian, it's not very successful. So this is the first non-trivial eigenfunction. Whereas if you do it with the one Laplacian, then you get an almost perfect result here. Another thing now, more from single eigenfunctions towards decompositions, is to think about decomposing images like you decompose signals. So take this image on the left with the three simple circles, then I think that everybody would intuitively say there are three structures that I should find in this image: the big circle, the middle circle, and the small circle. And they are kind of three different frequencies or scales. So the large circle is the largest scale, so it's the lowest frequency. So if I do a decomposition and I have something on the lower axis that corresponds to a generalization of wavelengths, then the big circle should appear first in the decomposition. Then the middle circle should appear, and then the small circle should appear at later time. So you would say these are more or less atoms of an image. So you would like to have something like I depict here is more or less three deltas of different wavelengths that give you these three parts in the image. So how could we get something like this? Well, one thing that is easy, well, it's not easy, but natural to look at, is the total variation. So again, the one Laplacian, if you want. So here is the formal derivation for C1 functions, or W11 function as the integral of the norm of the gradient, or the correct dual definition. And this model is very popular since now about 30 years in imaging. It's so common that you don't even talk about it much anymore. There is not much research left. And there is a time-dependent version of it, which is the total variation flow. So you start with the image you want to denoise, or as I would say, to decompose, and compute the total variation flow over time. So the nonlinear version of the heat equation. And then there is an interesting observation that has been made in the last, or there are several interesting results in the last 20 years, starting with the work of Cassel. Namely that, first of all, it is a matter of the different scaling between the one Laplacian and the time derivative on the left-hand side. The total variation flow only exists for finite time, and then the solutions are constant, namely constant in time and constant in space. So you converge in finite time to the mean value of the initial image. Frequently, this is assumed to have mean value 0, so then you would say you converge to 0 in finite time, and this is what people call finite time extinction. Oops, there is a problem here. cannot share again. Does it work now?
Yes,
Okay.
It does.
Okay, there was something broken. Okay. And there was another interesting observation is not only that you have this finite time extinction, but interestingly also what happens in this finite time. And if you use a, my mouse is gone. Here it is. If you use a non-linear eigenvalue in the sense that lambda times f is an element of this set-valued operator, so this would be in the linear case correspond to minus Laplacian. In the non-linear case, you take the subdifferential of the total variation, and then you can compute this solution explicitly. You can compute, first of all, the extinction time, which is 1 divided by the eigenvalue. So again, you relate eigenvalue to scale. So if the eigenvalue, or well, essentially to frequency. So if you have low frequency, the eigenvalue is small, and then this flow exists for longer time. So that's what you observe is that small scale features are filtered out in much shorter time. And you can compute the solution explicitly. It's just a multiple of this eigenfunction with this linear decay until to the extinction time, and afterwards you are 0. Okay. And then there was, I have to mention this since it's the results by a Fields medalist. There was a result by Monforte and Figalli about the one-dimensional total variation flow, where they looked at a very simple solution actually of the total variation, namely something that is non-negative in a finite support, so in one interval and 0 outside. And then they can compute the extinction time as the mean value of this function. And they can characterize the extinction profile, namely as an indicator function of that interval where you have the initial support. So if you rescale, so somehow this limit, capital T is the extinction time. If you rescale this limit, this is somehow the left time derivative of the solution at the time of extinction. And this converges to the multiple of an indicator function. And this multiple is just 1 over the extinction time. So again, the eigenvalue in a sense. And indeed, we could show that, again, this means, well, it's easy to understand that this is an eigenfunction for the total variation, piecewise constant in 1D. It turns out that the solution, this is more or less always true for some evolution problems that have the same structure as TV flow. You always converge in finite time to something which is an eigenfunction of the functional in this sense, so that a multiple of this element is in the subdifferential. Okay, and just to show you, well, how it would look like. So TV flow would go from the lowest image on the right up to the first image. So this would give you from finest scales to coarsest scale, or if you go in the other way, you start from some coarse scales, more or less the mean value, and then you increase the scales, and you see that nicely, kind of first you have all the basic structures in the image, and then more and more finer structures like the eyes, the nose, and so on appear until you get the full image. And if you look somewhere in differences between images, you see what structures are added during this kind of decomposition, in this case, a decomposition over time, in finite time. So now that I've told you about spectral decomposition, let's just go back to the basic question. What is actually a spectral decomposition? And so let's go back to the linear case. We know from basic functional analysis what is the spectral decomposition of a positive definite or semi-definite linear operator. Okay, in the most general case, if it's not compact, you can't do it as a sum, but you have just a spectral integral. So what you have is an integral over the possible spectrum R plus of, well, some function of the eigenvalue times a spectral measure E lambda. So this is somehow a measure at each possible value of the eigenvalue. The relation to our setting is we'll speak about functionals. So what we say is if you have a positive definite operator or positive semi-definite, it is actually corresponding to a semi-norm. So the bilinear form created by that operator is a norm, and the square root is just, or is a semi-norm, depending whether it's definite or semi-definite, and the square root is always a semi-norm. So we could also say, in some sense, the spectral decomposition of a linear operator in this sense is equivalent to the spectral decomposition of the semi-norm in a Hilbert space. Okay. Now, this cannot be generalized since the operator is not, if the operator is not linear, but you could say, okay, I'm a bit more modest in a sense. I'm not interested maybe in the spectral decomposition of the whole operator, but maybe I'm happy with just having a decomposition of the application of the operator or some function of the operator to specific elements. So if I'm happy with this in the linear setting, this means I take a scalar product of this measure with f, and I have a vector valued measure only in the Hilbert space. So this would be a measure in the space of operators. Now I have a measures in this specific Hilbert space. And then I can say, okay, maybe I can generalize that. So if for each f, I have here some measure that decomposes into basic eigenfunctions. Okay, so that's the main idea. The change is, of course, if you have the decomposition of a linear operator, it does not depend on what the f is. So this means it's independent, for example, in the flow, like in the gradient flow, it's independent of the initial value. If you do it in this way, then this measure that you get in the end may depend actually on the value f. So in the total variation flow, if I compute some decomposition of this, like I will show you in a minute, then it will depend on the initial value. You get a different decomposition and maybe different eigenfunctions for different values of f. Okay, so this is how we defined a spectral decomposition 5 years ago. So we said we want to have for each f a vector valued measure, and this should have two properties. It should preserve that eigenvectors or eigenfunctions are atoms. So if I start with an eigenfunction in this sense again, so lambda f is in the subdifferential, then I only get the spectrum at one well-defined value, namely the eigenvalue. So this is a Dirac delta at the eigenvalue in this artificial time variable s, or in the spectral variable s. Okay, so this is what you expect. Like if you put the Fourier decomposition of a sine function, then you only get one entry at the corresponding frequency. And then, of course, we want to have a reconstruction formula. We want for every f to be reconstructed as the spectral integral. Okay, and then you can say, well, this is maybe the frequency representation, and as usual, you can map between some kind of frequency and some kind of wavelength. So wavelengths would be 1 over s. It's often a bit more convenient to talk about this representation in the wavelength. So it's a little bit of rescaling, and you go from s to 1 over s. Okay. Okay, and there's also something interesting. Once you define this, you can do a polar decomposition of this vector measure into something of unit norm. This is the phi tilde, and some scalar measure, some positive scalar measure. And then you get actually a generalization of the Parseval identity. So the norm of f squared can be computed from the spectral integral. So you just have to take here a scalar product in this Hilbert space with elements of order 1, and then integrate over the scalar measure. Okay, so this is what you're used to somehow as the Parseval identity in the linear case. Okay, and of course, this works in the linear case. If you take, for example, the Laplacian eigenfunction is a special case of the linear operator I had before. So J would be this thing. So then we get the Fourier decomposition as a spectral decomposition out of this. Now we can be more general and say, okay, we go to all kinds of, well, essentially you can always think it's a semi-norm. So what we need is functionals on a Hilbert space that can always also be infinite, that should be convex, somehow lower semi-continuous. And the important thing is they should be absolutely one homogeneous. So this is exactly the property like you have for a semi-norm. So if you take a multiple of u, you take here the absolute value of this constant times the functional of u. Okay, and then we can define the effective domains where the functional is finite, and we can define the null space where the functional is 0. And it turns out this is really a null space in the linear vector space sense. So this is really a linear space that you can kind of filter out, so we won't care too much about it. Okay, here's some basic results. If you have functionals like this, they are automatically non-negative. This is a consequence of the one homogeneity, the positive. Then you have actually a triangle inequality, and you have this kind of invariance with respect to the null space. So if you add, as in the linear case, if you add an element of the null space, it does not change the functional. And you can show that the dual functional is the indicator function actually of the subdifferential at 0. So somehow the subdifferential at 0 is the nicest case, and under a weak regularity assumption, actually the subdifferential at 0 includes always the subdifferential at any other point. Okay, so if you think about the simplest example, the absolute value, then the subdifferential at 0 is exactly the full interval from -1 to 1. For the subdifferential for any other value is just a subset. In this case, it would be just -1 or +1. So it would be a subset of this subdifferential at 0. Okay, and we can prove in general that if J is in this class of absolutely homogeneous, one homogeneous functionals, then it is always also the dual of some indicator function. So there is a pre-dual under the assumptions we made. And this set K is symmetric around 0. So K is the same as -K. Okay, and the subdifferential at 0, so the largest possible subdifferential is the closure of the convex hull of this set K that you have here. Okay. And there is an interesting characterization of subgradients, or a necessary condition. If you have a subgradient, then it's actually in the boundary of this set K and orthogonal to the null space. Okay, this is really a space, so there is a orthogonal complement in a Hilbert space. Okay, so we have defined, now the question is, how do we get an eigenvalue, so an element such that lambda u is in the subgradient of this functional at u again? And there is one thing that we called ground state in the first paper with Martin Benning. So what you do is, like you do in physics, for example, for the Schrödinger equation, you take the energy J and you minimize it on the unit sphere. And we also, factor out here the null space of the functional. So we stay orthogonal to the null space. So you could say some of the null space are the trivial eigenvalues and eigenfunctions, which we don't want to have. So if we minimize that, then we can define lambda 0 as the function value at this minimizer, and P0 a corresponding subgradient. And here it's important not to take an arbitrary subgradient, but we take the one of minimal norm. And then, or no, vice versa, we take P0, actually is lambda 0 times U0, so times the minimizer, and then it's an element of minimal norm. And in particular, it's an eigenvector. It turns out this is actually the eigenvector for the smallest non-zero eigenvalue. This is why we call it ground state. So under very weak conditions, so basically if there exists a minimizer of this functional on the unit sphere, these are also the typical conditions for existence of variational methods or TV flow, there exists at least an eigenfunction. We are not talking about the empty set. And then there is an interesting geometric characterization that you can make. And it's basically about the geometry of the space and its dual space. So an element is an eigenvector with some eigenvalue if the corresponding renormalized P, this will become the candidate for the subgradient, this must be an eigenvector with eigenvalue 1. And if P is an element of minimal norm in this set. So this gives an interesting insight. If we want to have eigenvectors, these are always elements of minimal norm in some subgradients. Okay, so elements that are not of minimal norm, if you have multi-valued subgradients, they are not interesting because they cannot be eigenvectors. Okay, and then there is another interesting condition that gives a geometric insight. If you have this set K, for which, so somehow you can think this is the sub-differential at 0, then P is an eigenvector if and only if you have this relation. So geometrically, this means as follows: for all Q and K, this is greater or equal to 0. So what you do is you go to P, you compute the tangent to the set K, and then you check whether K, you compute the orthogonal to this line here, and then you check whether this is kind of a tangent, so whether K lies on one side of this set. So in other words, if you compute the tangent, you have to check whether the tangent is orthogonal to this line to 0. If you have this kind of situation, then you get an eigenvector for, in this case, always for the eigenvalue 1. Everything else is a rescaling. Okay, so if this K has a nice shape, then everything is okay. If this K is very degenerate, I mean, it's still a convex set, so it's probably not too bad. But if it's a quite degenerate convex set, then you start having problems, and then you don't have an eigenvector. Okay. Okay, this is just saying again the same thing as before. Now that we have understood some basic properties of the eigenfunctions, let's check how we could define spectral decompositions. There are several options. Either you solve the variational method, or you solve the gradient flow with initial value f, or you solve the inverse chaos space, which I don't explain at this point. And then you look at the whole time evolution, either of the variational method or of the gradient flow, and you compute the second time derivative and you rescale it appropriately, and then you get the corresponding phi in the spectral decomposition. So this is how this would look like for an image of some stones, you see the first element in the spectral decomposition is basically the mean color. Then you start to having the large stones, then you get also the smaller structures, and then you start having all kinds of textures at smaller and smaller scales if you compute this phi for the TV flow. Okay, why is the TV flow particularly interesting? Well, the reason is this old theory about gradient flows by Bressis, or actually about maximally monotone operators. So here, instead of A, you could have this subdifferential. This is a maximally monotone operator. And the important thing that the Bressis theory, which I won't recall in detail, gives you is that actually a solution of this is actually a solution of the equation below, where A0 does a particular selection. It always chooses the subgradient of minimal norm, or the element of AU of minimal norm. In our case, this is the subgradient of minimal norm. And we have shown below an element can be an eigenvector only if it is a subgradient of minimal norm for some P. Okay. And then we can check what happens. There is an interesting thing, an interesting orthogonality relation. So if you take time increments, if there is a spectral decomposition, then they are orthogonal. Okay. And we know the condition from before that we have to check, and you can check that for the 1D TV flow, this geometric condition. And it turns out, well, there's a little lemma that I don't discuss in detail, but it turns out indeed the one-dimensional total variation flow gives exactly a spectral decomposition. So at least in 1D, we can be sure that this is an exact spectral decomposition in the sense of our definition. In 2D, cannot show this for arbitrary data, but at least numerically, it looks very good what we get. Okay, and there are some generalizations that we can make. Something which is very easy is the L1 norm. And then there are two generalizations of kind of the 1D TV. I think the first is really the right generalization to multi-D. So we take not the total variation, but we take the divergence of a vector field. This has a very similar structure. You can also take the integral of the absolute value of the rotation of a vector field. Also, this gives you a spectral decomposition. And since they are orthogonal, that can be used to have a decomposition also for the sum. So if you have look for something with sparse divergence and sparse rotation, then you also get a spectral decomposition, which we think is quite interesting because that opens a way to have some kind of orthogonal or spectral nice decomposition into divergence parts and rotational parts of a vector field. It's just in general for us, at least for me, a bit difficult to interpret the videos of the vector fields that we get and these images, so I don't show you too much of these. I just show you some other examples which are a bit more easy to understand. So there's been a lot about one Laplacian and generalization. Another example is actually the infinity Laplacian, or actually the energy corresponding to the infinity norm of the gradient. You can do that either for the classical gradient, or you can also do that on a graph. So for the graph derivative. It turns out if you do this for the classical gradient and you do this like in L2, then the ground state of this problem, so minimize the infinity norm of the gradient with u having zero boundary conditions on some set, gives you exactly the distance function to this set. Okay, so what we have from that theory is actually a generalization of distance functions to graphs. And well, here's the corresponding result. Maybe that's not so interesting. Maybe it's interesting, more interesting to look at images. So what Leon built was a graph structure of United Kingdom, I think weighted by habitants, and setting the function to 0 on the boundary of United Kingdom, which is increasingly difficult to define nowadays. There you can compute somehow a nice distance function, and you can check well, the people in London may like this, that basically London is very close to indeed the maximum of the distance function. So it's like the central of the UK. I think Oxford is also quite close to the maximum, whereas Cambridge is not. I leave it to the people in Cambridge to think about it. Okay, or you could have, like in this case, define kind of a distance function on discretized manifolds. So would look in this case like this. So here we have this marked point below to which we compute the distance. It looks naturally, so there is small distance here and large distance very far away. Okay, now finally, let me show you some imaging applications that are even easier to understand. So this is now all based on total variation flow. And remember, we have this reconstruction formula in a sense. If phi is roughly the spectral measure, then we integrate the spectral measure from 0 to infinity and we get back the function f. Now we can easily do filtering once we have this spectral decomposition. If you have a spectral decomposition, as in the linear filtering case, you multiply with some filter to damp out or to amplify certain frequencies. So omega would be that filter function, and then you can compute stuff. So of course, a trivial thing you can do is start to do, to make people younger, at least on images. So this is Michael Möller's grandma. She was so nice to devote her picture to us. And if you damp out the corresponding frequencies, you see, you get, well, rid of a lot of wrinkles without losing the natural way the image looks like. Okay, that was the easy part. You can ask the opposite questions. You can try to make Michael Möller look old, which is something we tried to do since many years. And what we did to make it natural was to use the wrinkles of his grandma. So exactly the spectral part we have filtered out here. We were registering the faces and then introducing the wrinkles here, and you see at least 20 years from the first picture to the second picture without losing any natural geometric appearance in these images. Okay. And so you could think about other applications. One would be for the people like computer games, to have your personalized avatar. So you take the structure from your face and map it to the avatar to get something realistic. Okay, or you could just make fun and have tools for automated fusion of images. So, okay, here the spectral decomposition is only the last part. Of course, before you have to detect faces, detect landmarks and register them and segment the faces. And then you could start changing like texture of Reagan onto Obama or whatever you want. And you could also do something that I didn't mention so far. Of course, you could also introduce local filters. So far I was putting a filter on the whole image. So either take the full spectral part, but you could also make it spatially local. So take a different filter in the eye and mouth regions. So you can say, okay, I take Reagan's eye and Obama's mouth, or vice versa, and see what you can get. Or in this case with George W. So you see here, for example, the mouth and eye regions have been changed. And you can get all kinds of these kind of combinations just to play around. And it's an interesting thing is that this is quite robust. Actually, with one filter setting, we could do so far all American presidents. Maybe there was a bit of too much of orange for the last one, so there we did some other things. You could also do very non-standard things in image fusion, not just fusing face image to face image, but maybe fusing face images and some sculptures to have some, well, something that some presidents would have liked to be on Mount Rushmore or in ice sculpture. And you see, you still have a very apparent geometric view of these images. Okay, and well, since it's just 3 weeks to Christmas, you can also ask historic questions. Is the American Santa really related to his historic original Saint Nicholas? And you can try to see what happens if you exchange, for example, their face regions here. Just going back and forth, you see the differences. Okay, and you can do other things like having your favorite image, digital image, look like a painting of your favorite painter. So here, for example, we were extracting some appropriate spectra from a Monet picture to get the kind impression of a brush stroke, and then just introducing it into a digital image to make it look like a piece of art, hopefully. And there's all kinds of things for the future that you could still think of once you have these methods for basic filtering. And just to finish, there's of course a lot of generalizations. Actually, Martin Benning was strongly arguing that you shouldn't generalize this for arbitrary methods. So for example, for inverse problems, you could have an arbitrary regularization method R with some parameters alpha, and then you basically could start looking for eigenfunctions of these regularization methods, which is still fully consistent with our setup that we've considered so far. And a recent work of Leon with Guy and others was even computing or trying to characterize eigenfunctions of deep neural network, which are a certain kind of reconstruction. So now with even having mentioned deep learning, I think it's a good point to stop. Thanks a lot for the attention.
Thank you very much, Martin. It was really, really interesting. So I just asked the audience to write their questions on the chat or on the Q&A, and I will read them. Okay, so I have a couple, but I'll start reading first the one we have from the audience. So Patrick Fuchs is asking you, could the decomposition into divergence and rotational parts be used to decompose, say, electric fields into divergence-free and other parts? For instance, separate the background and source-related components?
Yes, that is one thing we were thinking of. Actually, it depends on what functional you use. Of course, you get kind of, if for example you take the divergence, you get the part with small divergence. Actually, you get even more. So you could say you get up to, well, at the extinction time of that flow, you should get a divergence-free vector field, and before you get somehow the largest divergence component, the largest scale divergence component in that vector field. Mm-hmm. We were just too shy to show pictures, since for us it's really, well, unless you do it on very, very simple examples. On real world complicated vector fields, our eye, at least for Leon and me, has had problems to interpret the results really nicely. Mm. So I didn't show them here. But if there is some expert on that, he might be able to see things that we don't see. So I'll be happy if somebody can help me on that.
So you mean for the real world examples, it's very difficult to tell whether you get all the way to divergence-free fields, or the decomposition makes sense in that sense?
Yeah, so what are the results that you get? So what are these spectral? I mean, we know these are eigenfunctions of the divergence part and of the other part. But I don't know, I mean, we didn't learn to interpret them. Divergence-free is okay. I mean, in the end you get a divergence-free, but actually we would get much more, and we cannot interpret the part we get more.
Okay, interesting.
So
Thank you.
Yeah, if you just say you want divergence free, I would say there are simpler methods to do it.
Yeah, of course. Yeah.
There is one other question from Guozi Dong. Can the eigenvalues be separated, or the eigenfunctions associated, or are the eigenfunctions associated to unique eigenvalues, for instance, for the TV case?
Yeah, that's a good question. There is, first of all, the non-trivial question how you define eigenvalues, because there is a scaling problem. So our way to do it is to say we take functions that have norm 1 in the Hilbert space and take the function value of this. So kind of we take the Rayleigh quotient to define the eigenvalue. That's maybe the right thing. So J divided by the norm, so that you really have 2 homogeneous functions. So in that sense, the eigenvalues are separated. They really are ordered increasingly by scale. But in general, they are not simple eigenvalues, if that is the question.
Mm-hmm.
So the question is what, I mean, the question is much more difficult to answer actually than in the linear case. In the linear case, you know, if you have a non-simple eigenvalue, then there is a linear space spanned by the eigenvectors.
Yeah.
In the nonlinear case, this is not true. So there is, for example, if you think about total variation in the whole space, there you can give simple examples. You take you take the image of a black ball on white background. So all black balls of same radius will have the same eigenvalue, no matter where you shift them. So there is a lot of non-uniqueness, but of course the linear combination of two such images is not an eigenvector in general, or an eigenfunction.
Yes. And so I would like to know, like, the norm, which norm are you using for the TV case, where you use to define this unit vector, unit eigenvector?
So it's always, I mean, you define it. What we do is we define the total variation from the beginning in some Hilbert space. So the canonical choice would be L2, but you could also choose others like H-1 or something like this. Then you get different eigenfunctions and eigenvalues depending on what Hilbert space you choose. So from the very beginning, we pose the problem in a certain Hilbert space. We also compute the subdifferential in that Hilbert space, and we also compute the Rayleigh quotient with respect to that Hilbert space norm. Of course, L2 is the one where you can do simple computations.
Okay.
But there are also others that would be interesting.
Mm-hmm. So my question actually is that if you have for instance, if you have ball which has a bigger radius, and you might also have another ball which has a higher intensity. So are they belong to the same family of eigenvalues?
Yes,
of eigenfunctions?
Yes, there is also one invariance. I think it's even in my first paper with Martin Benning, we computed that, or I mean, the example can be found much earlier. It's just writing it as in terms of design values. So there is one, I think, something like height times radius or divided by radius. No, I think it's height times radius is equal to 1 over eigenvalue roughly.
Okay.
So then you see, of course, you can scale a lot, but I mean, the height I would not be concerned so much by the height, because you have this kind of non-uniqueness also in the linear case of multiples. But of course, you cannot translate things typically in, or you have some other kind of non-uniqueness in the linear case.
Yeah, thank you.
You're welcome.
I have a curiosity. How does this extend to higher order regularization? Is there any theory on that, like TGV?
Yes, actually, Martin Benning's PhD thesis, which I recommend to read. There are several, and then there's also the one paper we had with Jan Müller and Christoph Brune on higher order TV. There we computed several eigenfunctions. So for TGV, it's interesting. It depends on the weighting parameters between the first and so let's just keep it with first and second derivative. Okay, otherwise it will be a bit too complicated to discuss. But then you weight somehow in the informal convolution part. You give a weight on the first and on the second derivative. If one of the weights is too high, you only get basically the eigenfunctions of one of them. And if I remember right, it was a particular challenge for Martin Benning for some time to find an eigenfunction of TGV, which is not an eigenfunction for the first or a second order derivative. But if I remember right, there is at least one. But the good news is that typically both the eigenfunctions of, if you scale it right, if I remember, then you get both the eigenfunctions of TV and second order TV.
And is there any filtering application with these eigenvectors of TGV? It would be just interesting to see how they differ. Like,
I mean, you can do all these filtering. Well, I mean, applications. I mean, the applications I showed you so far is basically some games we played just to have fun, to be honest. I'm not sure if we have a really serious application so far. Basically, you could do everything we do with total variation, also with higher order things. For the eye, again, the same as with vector fields, it gets more difficult to interpret this stuff.
Yeah. Okay. So maybe some of the questions from the audience. I have like one quick last one. Numerically, how do you compute these the eigenvectors? Which algorithms do you use?
Well, numerically, this is also an interesting question how to do it. So the simple thing to do for the spectral decomposition is just to compute the gradient flow and discretize in time, and approximate the time derivatives by finite differences. Which is not so bad for TV or things like this, because mainly the most dynamics is locally piecewise linear. In any case, even if you don't have these geometric conditions that you need for the spectral decomposition, what you can do is go to the extinction time, and at the extinction profile, so the rescaled value at the extinction time is always an eigenfunction. So you could take this, subtract it, and start again, which is not extremely efficient. So
okay, I see.
There is also some kinds of nonlinear power methods if you just want to compute. I mean, that's also the question what you want to do. Do you want to have a full decomposition, or do you just want to compute some eigenfunction? Like in these graph clustering examples or in these distance function graphs, we basically want to compute the ground state. So you can do it more directly with a power type method to compute.
I see.
Some eigenfunctions.
Yeah. But if you want them all, of course, maybe getting the profile for all of them will be inefficient.
You never get all of them because there is an even for 1D total variation, there is an uncountable number of
well, many.
But if you want to decompose a specific signal or image into eigenfunctions, then you can do that with the probability.
So I have another question actually. So is the ground state to be unique, or?
In general, not.
It seems can be scaled arbitrarily, or?
Yes. Well, okay. We define the ground state to have norm 1 in the Hilbert space, so there is no scaling. But then it depends kind of, for example, if you think about total variation, of course, it depends on the symmetries that you have. So if you do it on the whole space, you have this problem that you have the grounds. There is actually no ground state. I think on bounded domains, I don't know any example where you have a non-unique ground state. It's kind of always the nicest structure. But there's no proof that there is some kind of uniqueness of that shape.
Okay.
But I haven't seen any example where we can compute more than one.
Interesting.
There is one final question maybe from Eric. Eric, do you want to ask it yourself? You can unmute yourself and just ask.
Yes. Hi, Martin. Very nice talk. Thank you. I was just wondering, is there a way to get error estimates when you, for instance, when you want to do a reconstruction? Do you know in advance how many modes you should compute, and do you have estimators?
Yeah, that's really a bad thing for the nonlinear. I think we can never say how many modes we use. We can only say up to which frequency we need to go. So the frequency is kind of related to scale. The problem is, due to this nonlinear data dependent decomposition, we cannot say before how many modes we will get until we get to a certain point.
You compute them, right? Okay.
So in this sense, the answer is no, we cannot say how many we get. We can do some kind of estimates, but they are not, there is no estimate on the number of modes. That's
okay.
Issue.
Okay, so I think we're a little bit over 5, at least in Europe time. So we thank Martin again, and we hope to see everyone again next week for our last session before the Christmas break. So thank you very much again, Martin.
Yes, thank you.
Thanks, Martin.
Thanks.
Have a nice evening, everyone.